Good morning, everyone. Welcome to part two of mapping crime data in R. This is the hands-on coding, which will be a live code demonstration run in RStudio. Uh, just to reintroduce myself, my name is Nadia Kennar. I'm a research associate with the UK Data Service based at the Cathy Marsh Institute at the University of Manchester. Just going to give it a couple more minutes to let people join, and then we're going to get started with some introductions and then get started with the code demonstration shortly. So yeah, just going to give it a few more minutes for people to join. So yeah, in our code demonstration, which can be found on our GitHub link, which I believe Emma or Louise have pasted in the chat. But we're going to be covering four main topics. We first start by looking at a very descriptive analysis of crime data and creating some point patterns. We'll then move on to understanding our shapefiles, and this is where our coordinate reference systems and our projection methods come in handy. We'll then move on to combining our census data, and this is basically to start mapping crime rate as opposed to mapping the raw crime data. And lastly, we're going to be looking at our spatial relations, which involves the spatial interpolation. We do have some extra topics, including how to make interactive maps via leaflet, but depending on time, we'll see if we can get to those or not. So yeah, just a reminder, here's our link for the GitHub. And I will go ahead and end this slide and move on to just quickly reminding you how you can access the code yourself. So if you make your way over to the GitHub as seen here, and you work your way into the code folder, you'll see all the content that we need for today. There are two ways to obtain this. There's two options to run the workshop. The first is to run locally in your own RStudio, and this involves downloading the files and running them on your computer. So yesterday I demonstrated how to clone this to your own computer. You can also just download the whole folder as a zip file and install this into your R. But this would mean that if I make any changes to this GitHub, you won't be able to see them without having to re-download the whole entire folder onto your computer. The far easier option is to open the crime mapping workshop, which I've just got over here. Let me just move that across. And this will get you something that looks like this. As Louise has mentioned in the chat, and as I mentioned yesterday, you should have pre-installed or pre-run this cell here, which installs our packages into R. As you can see, it took mine about 38 minutes to install, and unfortunately, this is just the limitation of Colab and working with spatial packages, because they require certain independent dependencies to be installed onto this software. So yeah, hoping that everyone has gone ahead and done that before this workshop. I'm going to be running the main demonstration in RStudio, and Louise is going to be manning the Colab notebooks. So yeah, any questions for those, pop them in the Q&A, and myself and Louise will do our best to answer those as we go. So just to make sure that everything is working, you can go ahead and load your packages. You will see an error that says there is no package called GeoJSON.io, and that's absolutely okay and absolutely okay to ignore. But again, working with Colab, you have to kind of come up with these really annoying workabouts to allow these spatial packages to create visualizations in Colab, and this is just something that you have to have installed, have present on your Colab. So yeah, I'm going to move on to the topics now. And I'm going to move this back over to RStudio. So here we have sorry. Rid of those. I'm just going to clear my environment so that you can see exactly how do I do this. Sorry, 1 second. There we go. Right. So as you can see in RStudio, we have four main panels. You have this main panel, which is your You have four main panels. This is where we'll be running most of the code, this panel in the top left. You can also adjust the size of these panels to see, depending on your preferences. And on the bottom left, you have your console, and this is typically where the output of the code will be stored. But because we're working in our Markdown script, the code and the output can be seen within this main console here. The panel on the top right shows your environment. So this will show anything that we create in R or anything that we download to R, including our datasets, will be present here. And your panel on the bottom right, this is your files and plots help panel. This just basically shows you all the files that you have from that folder. So you can see that I'm currently working in a folder from my home into documents in our mapping crime data 2025 folder, and I'm currently looking at the code. You want to be working within the crime mapping underscore workshop.rmd file. You will also see that these four topics have been split into their individual R Markdown files as well. And this was just for ease in case this file was just a bit long. If you open the outline, you'll see that there are lots of topics covered here. So I understand that it's going to be a bit overwhelming. So you can work within the individual script files as well. But if you're in Colab, you'll need to be working with this one. So let's go ahead and get started on the code demonstration. I'm also just going to turn off my camera because I'm getting distracted by my face. So we want to make our way down to your load packages. As always, you always need to load your packages before doing anything in R. I've already installed my packages above, so I'm just going to go ahead and load these. And you'll see that those have been loaded in our console. So our first step is to explore the crime data. Before doing this, we need to load in our crime data set. We'll be using the data from the data.police.uk. And specifically, we're going to be looking at data from 2023 to 2024. And just while we are in topic one, we are specifically going to be looking at only the month of February. So if you go ahead and run this code, this is basically just connecting to our GitHub folder called data and ensuring that we download that specific month of data into R. And then also using this function called janitor clean names, which basically just, as it says, cleans the names, and it makes all the variable names lowercase with an underscore between any names. There are two ways to view data sets in R. One is simply by clicking on that object. So as you can see, there's been a new object created in our environment. If you click this, you'll see our crime data set here. We have 6,806 observations. So that's 6,806 reports of crime in the area of Surrey in February 2024. And you can see that we have 12 variables. We've got this crime ID, which is a unique reference number for each crime type. We've got the month this was recorded in, where it was reported by, what area this falls within, the longitude, the latitude, the location. We have the LSOA code, LSOA name, and this is our lower layer super output areas, which is a geographical unit that governments use to basically group crimes. We've got the crime types and the last outcome category. You can also view this by running the functions head and glimpse. So the head function brings up the first 6 rows of the dataset, and this is easier. If you're working with a really large dataset, it's good just to view a small portion of that dataset so you don't get too overwhelmed. And the glimpse function basically provides this in long format, but it gives you a nice list of all your variables that are present here. Yesterday, we talked about our points, lines, and polygons, and these being the 3 main components of a vector dataset. In our data here, if we go back to the head code, you will see our coordinate variables, which are here, our longitude and latitude. These are our point data. These are our point data. So this is one point in reference that tells us where this crime was reported. The location variable is uh, sorry, represents the lines. And this is normally defined by a street or a junction, as you can see here. And the LSOA name represents our polygon. And this is like a borough, a ward, or a district. It's basically like an enclosed area. And yeah, this is just a unit measure in census geography. So that's just some guidance to our points, lines, and polygons data and how they work. So we can use the unique function to basically create an array of the different possible values in the column. So as you can see, I'm calling on our crime data set and I'm using the $sign symbol to then call on our variable crime underscore type. As you can see, this lists 14 different types of crime types in our data set. We're only going to be exploring a few of these today, just to understand, just as an example. Um, but yeah, before moving on to some of the more like complicated spatial techniques, let's go ahead and create some frequency tables to basically understand the distribution of these crimes. So in R, they have a few base packages. These are packages that are automatically installed and downloaded into R. That means you don't need to like install any extra packages. And this comes from this function here called table. So what I'm doing now is creating a new object called counts, calling on the function table and calling on our crime type. You can go ahead and run that. You then want to basically put this in ascending order. So I'm going to be doing this from the highest crime type to the lowest crime type. And then I'm just simply asking RStudio to print those results. As you can see, we now have the number of crime types for each offence listed in our table below. So we can see that violence and sexual offences have the most crimes, with drugs having the least crimes. We can also then go ahead and put this into a visualization. Again, we're going to be doing this using RStudio's base packages, and this is under the functions par and bar plot. So I'm just going to go ahead and run this whole chunk of code. As you can see, we have a fairly, let me just get that out of the way. Yeah, so as we can see, we have a very like simplistic visualization, a very simplistic bar plot, arguably quite messy and not that nice to read. And this is one of the limitations of the base packages in R, in that they become quite hard to basically create that aesthetic that you want. So what we can do instead is use our ggplot package. And this is a very, very common package that is used for visualization in R. What I'm going to do here is create a new object called crime summary. And I'm doing the exact same thing by selecting our crime type, sorting this by the highest value, and then selecting the top 10 crimes. And yeah, this is our ggplot function here. So actually, in fact, I will run this bit first so you can see. And there we go. We've got this like table column that shows all our crime types, right? And we're going to be using this object that we can see here to then make our visualizations. So you can go ahead and run this chunk of code here. As you can see, there are lots more aesthetics that are available that, allow you to make much more visually a pleasing plot. In this code, I am calling on the crime type again, reordering this by highest to lowest. And I'm also including a title, and I'm also labeling the X and Y values. I'm also using this code theme minimal, which just is an aesthetic that ggplot has that allows you to make nicer plots. So there we go. Now we've got a much clearer visualization of our crime types in Surrey from February 2024. This is much easier to read, and yeah, that was just a very simple ggplot example. Right. We are now going to be moving on to looking at our simple features and projection methods. Simple features is a common R language and it allows, also known as SF, which we mentioned yesterday. And this basically allows you to handle and manipulate your unit of analysis, i.e. your points, your lines, or your polygons. And these simple features allow you to store spatial objects. We mentioned yesterday that we'll be working with specific coordinate reference systems. And this is just used to locate geographical entities. So a spatial reference system defines a specific map projection as well as transformations between different spatial reference systems. And these are identified by what we call EPSG codes. So again, remember these projection methods allow you basically to move from the 3D to the 2D, and the coordinate reference systems allow us to identify these specific locations within these. Now, there are thousands of coordinate reference systems that we could use. The most commons are the British National Grid, the BNG, and the World Geodetic System, which we discussed yesterday. The World Geodetic System has an ESPG identifier known as the 4326. Now, when you're working with SF package in R, you need to be aware of what that ESPG identifier is in order to call on the correct reference system. You can find these anywhere online if you give them a quick Google, but also they are identified in the help packages in R. So our first step is to transform our ordinary data set, so that's that original crime data set, into an SF object. And what this is basically doing is going to convert our latitude and longitude variables to the correct geometry attributes. So remember, just to recap, these SF objects are just data frames that are a collection of spatial objects, where each row is a spatial object, i.e. a polygon. So the first step into doing this is we can run a function called the st_crs, which basically just checks whether our data set has a coordinate reference system attached to it already. If we run this code, we can see that the coordinate reference system is NA, which means we do not have a coordinate reference system attached. So we can go ahead and run this bit of code here using the st to _as_sf function. I'm also going to create this into a new object called SF because I don't want to override our original crime data set. I want to keep that as is and create something new. You then call on the function chords, and as I mentioned, we're going to be converting our longitude and latitude columns in our crime data set. We're then going to call this into the World Geodetic System, which is the 4326 identifier, and I'm also just telling it to ignore any NAs for now. Just as reference, RStudio is case sensitive, so our longitude and latitude columns, if we have a quick look again, these are lowercase, right? If you were to put these with a capital L, this code won't work because it won't be able to identify that correct variable. So let's go ahead and run that code. And then we're going to check the coordinate reference system of our new object that we just created called SF. And as you can see, we now have a coordinate reference system attached to our data. And this is identified here by that first line. The EPSG is the 4326, identified as the World Geodetic System. Just for reference as well, you might notice a difference in the two objects from crime and SF. Our original crime dataset had 12 variables, but our SF object has 11 variables now. And this is because we have combined the latitude and the longitude variables into one spatial variable that allows for the visualizations to be created. We can go ahead and check this by again running the head function. And if you scroll along, you'll see that we have this new variable called geometry, and it's telling us that we're working with point data. So this is a point data set. So let's go ahead and have a go at mapping this point data. Oh, a bit of a spoiler there, sorry. We can use ggplot intertwined with SF to make our visualizations, which is a really cool function in R. And what we do is simply call on ggplot. We use this function called geom_sf. And this is basically a unique aesthetic, and it expects to find an SF column containing our simple features data, which we now have defined by that geometry. You'll also notice that we don't need to specify the exact variable to use when using geom_sf, and this is because it basically automatically detects that new spatial geometry column. So let's go ahead and make this plot. So you can see that we have this rather vague but rather interesting plot of our crime data. So what we're doing right now is plotting all crime data in the area of Surrey. If you're not familiar with Surrey, you might be a bit like, well, what am I looking at, right? There's no further information. There's simply just crime data plotted on a call it an empty reference map. So we can go ahead and extend these plots. We can firstly include aesthetics to color the specific crime types, and this will give us something that looks like this. So this is getting a little bit more readable now. We can see that the distribution of the different crime types in the area of Surrey. You can also add titles, and you can also add or change the theme and the transparency. So let's just have a quick look at what that'll look like. So this is what happens if we add a title. Again, it's getting a bit neater and it's a bit easier to understand. And we can also change that theme so you can see the difference in the background. And these are important things to think about when you start to like present data, especially when it comes to like accessibility issues. So just something to consider. Using that theme minimal is important for that. But yeah, as I mentioned, these maps aren't really showing us, where in the world this is happening, right? It gives us a very blank northwest grid, but doesn't really tell us much more about where exactly this is, or doesn't visualize where exactly this is. And this is where we use our annotation map tile function. And what this basically does is overlay a reference map onto our thematic maps, as we discussed yesterday. And again, this is still using that same structure that we had before, but I'm just including another function here called the annotation map tile. So if we go ahead and run that, you'll see, there we go. That's our area that we were talking about, and this is the area of Surrey. So we've got a rather simplistic, but a very good, like introductory, explanatory visualization that shows us all the different crime types in Surrey from February 2024. You might also be interested in only exploring one type of crime, and you can go ahead and filter and subset for whatever crime type you're interested in. So in this instance, I'm going to be looking at the antisocial behavior. So I'm creating a new object called the ASB, and I'm using the subset function from R's base package, calling on our crime type. You use a double equal sign to select which crime type you're specifically interested in. And I'm going to create this into a new object. This select function is basically just removing any rows that don't include any data just to like neaten it up. And as you can see, we've got this new object now with only 1,059 observations. Again, just for reference, R is case sensitive. So if you had antisocial behavior with a capital B, you'll see that, I don't know why it does that. You can see that our object has now changed to 0. And that's because it can't identify that crime type that we were talking about. So I'm going to change that back to B, and I'm going to give that a run. That's fine. I'm just going to ignore the warning signs to update my packages because it's not necessary right now. So let's go ahead and plot this data now, the antisocial behavior dataset, onto a base map, also using the geom_sf file. So as you can see, we have a much like neater plot, right? We can start to see where exactly these antisocial behavior recordings or reporting, sorry, have happened in the area of Surrey. And just looking initially, you can see that, oh, they do seem to happen um, along what would be like transport links or main main roads. And yeah, so this kind of just gives us a pretty good introduction about how to start exploring our crime data and how to identify the correct coordinate reference system. I have a little activity here, which basically just gives you guys the opportunity to explore what we basically just learned. So I'm going to give you guys a couple minutes just to run through this activity yourself. You can do this in R and in Colab, they'll both work. And I just want you to basically compare this crime type to the crime type drugs. So your first step is to subset the data for those crime types recorded as drugs. Then you want to create this into a new object like we did for the ASB and name this drugs. And then we're going to use that ggplot function to plot this over a base map. So I'm just going to give you 2 or 3 minutes to fill out this little chunk of code here. And I'm going to see if we've got any questions from this section before we move on. I've realised I might have actually filled out this activity, so you've probably got the answers in front of you. So I'm just going to talk through these as they are. So your first step was to subset that crime data as those recorded as drugs. So you should have filled in that dotted line that should have been here, apologies, to subset this for drugs. If we go ahead and do that, you'll see a table that's been produced below. Oh, sorry, let's get rid of that. See our subset of data here. Scroll along, and you'll see that we have filtered just to our crime type drugs. If you had struggled to do this, again, it's just make sure that you're spelling it correctly, because if you use the lowercase d, then we wouldn't be able to find that specific variable type. We've then created this into a new object called drugs by using this arrow here. So this creates a new object, which has now been added to our environment. As you can see, this has 161 observations, which is correct if you remember our list of crime types at the beginning. And then what I've gone ahead and asked you to do is use the ggplot to plot the data over a base map or our reference maps. So just to recap, the function to do this is our annotation map tiles. And then you need to call on the new object that we've created, which is called, if I can spell it, drugs. And yeah, now we have this new map that shows our counts of drug reported crimes in the area of Surrey. And as you can see, there are far less compared to antisocial behaviour, isn't there? There's lots less clustering happening, there's lots less happening along the main roads. So yeah, this is just a great way to initially start exploring your crime data. But to take this one step further, this is where we move on to topic 2, which are known as the shapefile section. So we're going to look at how to read in a shapefile. We're going to then look at how we join this to our aggregated crime counts. And then from there, we're going to go and head and look at different classification methods as a better way to visualize these crime counts, basically to better understand those clusterings that we see happening in those original plots. For those working in RStudio, you can open this outline, table of contents, which just shows you a bit better, structure of what we're working through. But yeah, anyways. So again, make sure your packages are loaded. We don't need to do that right now because we've done this at the start of the workshop. If you're working with the individual files, then you will need to reload the packages each time. So a quick reminder, what is a shapefile? These are the common formats in a GIS industry, and this is where we store our vector data, known as our lines, our points, and our polygons. It stores a single feature, so that's the SF features, which means it will store a single type. The shapefiles the shapefiles contain multiple files that then represent all of the geographic data. There are 4 mandatory files to be aware of, which I've listed here. Um, and these four files contains not only the geometry for all the features, it contains the attribute for the features, but it also contains the correct coordinate reference system and projection information needed. Now, just to reference, in criminological research, the LSOA is quite frequently used as the main census geography. And we saw that in our crime data set, we do have the LSOA variable present. Typically, LSOAs, or our lower layer super output areas, they have an average population of 1,000. And these are basically used just to improve the reporting of small area statistics in England and Wales. It gives us a smaller unit of analysis, which, as we mentioned yesterday, will increase our variability within our results. I collected my shapefiles via the UKDS census support, which can be found here. If you're interested in how I've collected the data, there is a folder, there is a file, sorry, stored under the data folder, I believe, yeah, called downloading the data doc. So if you want some information about, how I specifically got that data from there, then there's a step-by-step process in that document. But yeah, let's go ahead and read in the shapefile for Surrey Heath. Again, I'm doing this by using a URL that links us to our GitHub, and we then need to list the necessary files for the shapefile. We then create the local directory for the shapefile, and we download each shapefile component. Typically, you wouldn't need to do all of this if you're reading in a shapefile that's stored on your computer. You would actually only need to run this line of code here. But because I'm working with a URL link, I had to do some further pre-processing to get that data onto here. So don't worry too much about this right now. But if we go ahead and run this chunk of code, you'll see that a lot is happening. And it says here, reading layer, the England LSOA 2021 census shapefile. It's telling us that this shapefile has 55 features and 4 fields. So it's telling us there are 55 different LSOAs in the area of Surrey. It's also telling us that this is a multi-polygon, and this is because we have all those 55 different areas and their boundary data stored within this one file. So what exactly can we do with this shapefile data? Oh, well, let's actually first just have a quick explore. So yeah, this is a bit more of a neater field, I guess. But yeah, this shows us the structure of a shapefile data. This is what we call a empty shapefile, and this is because we haven't added our crime data to this shapefile yet. But we can plot the empty shapefile to see what the area of Surrey would look like. So we go ahead and plot this. You can see that we have an area of Surrey with those 55 separate regions, those separate boundaries. Sorry, just making sure. Yeah. Obviously, this isn't telling us anything because it's just an empty shapefile. So what we need to do now is add our crime data to our shapefile data. I'm just going to skip over. Oh, this is just some information about how you would call on the specific spatial geometry column. So you can use the attributes variable, which just gives you a little bit more information about the geometry columns in itself. And you can also use the ST geometry column to basically split the feature and the geometry into two sections. So let's have a quick look at what that'll look like. So yeah, this just kind of splits the two columns into Right, so in order to move our crime data set on top of that shapefile, we now need to aggregate the crime data to our LSOAs. So if you remember, the original crime data set is a point data file, and that is simply listing all the crime types that have happened in that month. But we need to group our crime data by the LSOAs in that crime data so that we can add this to the shapefile. And this is because you would expect to see multiple crime counts in one LSOAs. You wouldn't typically just analyze individual crime counts. You would typically aggregate these to a specific area or boundary or postcode or tracks. Obviously, in this case, we're using our LSOAs. And in order to do this, we can run this very simple bit of code. What I'm doing here is creating a new object called crimes grouped by LSOA, calling on the original crime data set, not the shapefile, grouping these by our LSOA code, which is a variable in the crime data set, and I'm asking this to basically summarize this and count the number of crimes in each LSOA. So let's go ahead and run that code, and then we can have a quick look at what this will look like. So we have this new data set now that has two variables. This includes the LSOA. If we scroll up a bit. Yeah, the LSOA and then the counts of crimes that have happened in each of the LSOAs. So what we want to do now is merge that shapefile to the crime data set. To join the crimes per LSOA to the shapefiles, we can use the left underscore join function that basically returns all the rows of the table on the left side of the join and matches the rows for the table on the right side of the join. So again, I'm going to be creating a new object called Surrey underscore LSOA. Using this left join function, I'm calling on our empty shapefile and I'm calling on our new object, which is our aggregated crime count, and I'm asking it to match the LSOA variables in each column. So let me just break this down a little bit more. So if we open up the crime codes, crimes grouped by LSOA, we see our list of LSOA here, right? And then if you open up the which one? Sorry, the shapefile, you can see that we also have this LSOA code here, but it's just named a bit differently. This is just how the census tend to name their variables. So those are the two variables that we're basically trying to match together. So we go ahead and do this. And now we have this new object called Surrey LSOA. And you can see that this has now taken it down to 55 observations. So let's have a look at what this looks like. Now you can see that we have a corrected geometry. We have the aggregated crime count that we see in this variable count to our LSOAs. You can again view the geometry type by using the st underscore geometry, and you can also use the st underscore bbbox to obtain the object's value as specific units, but that's not too important to know. So great, now we have a working shapefile, we have a working spatial data frame. We've moved from a non-spatial to a spatial. Let's go ahead and see what this would look like if we were to map the data. I'm going to be using the ggplot package like we did in the previous section. Again, excuse me. Again, using the annotation map tile. So if we go ahead and run this bit of code, now we have a much neater image of our number of crime types in the area of Surrey. You can see that it's provided a nice gradient that shows which LSOAs have a higher number of crime counts and which ones have a lower number of crime counts. We can also improve this mapping again by adding certain aesthetics such as the scale feel variable and also improving that theme. So let's look what happens when we do that. Oh yeah, I haven't included the annotation map tile there, but yeah, kind of depending on, how you want to present your data, depends on which aesthetics you want to include. Okay, so we're going to move on to plotting via the tmaps package now, which is another package that allows for both static and interactive visualizations, which is a really cool function. It has a very, very similar syntax to ggplot, which makes it, really easy to go ahead and make these plots. You have the option to basically create two types of maps, as I said, static or interactive. And you can do this depending on how you basically change the function tmaps mode. So you can have tmaps mode view. So let's see what happens if we use the view function, which would be the interactive file. We'll go ahead and run that first chunk. Oh, sorry, yeah. So this is the interactive plot. As you can see, this opens up a plot that allows us to basically zoom in and zoom out and hover over certain areas, basically giving us a better way to explore these different types of crime types. Let's have another example here where we will be calling on the TM polygons function. And this gives us a much neater and like aggregated crime type for each of our areas. Yeah. And again, you can zoom in, you can hover, you can click, which is really cool. It gives us the names of the LSOAs, it gives us the names of the count, you've got the label. So, if you were interested in looking at one specific LSOA, then this allows you to do that. If we were to change this tmap mode to plot, I just want to show you how the map then becomes static. I should have updated my packages before, but I'm pretty sure I did, so this is just RStudio, unfortunately. Let that just run through. Yeah, so let's go ahead and run that static viewpoint and see what happens here. So we get that similar type of map. Let's go to the left. But this time, this is just a static image. You can't move, you can't zoom in. So the difference is up to you again. If you were presenting in a workshop or a live code demonstration like this, then obviously this map would be great for that. Or if you're presenting at a bit of research on a bit of paper, then a static image would be much more suitable. Okay, so now we've had a look at basic mapping. We're going to move on to classification methods. So how can we better visualize these crime counts? Well, count data does not equally represent the population distribution at hand, but tmaps allows you to alter the characteristics of these thematic maps via the styles function. And these different styles will result in different binning techniques. When mapping quantitative data such as crime counts, typically the variables need to be put into bins, as seen in the previous example here. The default binning applied to highlight the LSOA's group started from, that's incorrect, started from 0 to 5, 5 to 10, 10 to 15, and so on. And these bins were decided automatically, but we can basically alter these bins to alter the way that the data is presented. There are multiple different classification methods that you can use, but I'm going to be looking at three in example. And this is the k-means classification, the Jenks classification, and the standard deviation. The k-means is a method of vector quantization, and this aims to basically partition all n observations into k clusters in which the observations belong to the clusters with the nearest mean. The Jenks, which is also known as the natural breaks, aims to arrange a set of values into natural classes. Typically, this is like the most optimal class range found naturally, and this method minimizes the variation within each range. And then you have the standard deviation classification, and this is in the name, this is a standardized measure of observations deviated from that mean again. So by showing the values that are above or below the mean, this method will help to show which locations are above or below an average mean. So it kind of takes this plot that we're seeing, but increases its variability. I wanted just to show you a quick example before going on to those three classification methods, why it is important to show these. So this is a base package plot in R, which just allows us to run a histogram. Currently, the breaks are set at 30, right? And gives us a crime count distribution showing the frequency of crime count in Surrey LS in the Surrey shapefile. If you change the breaks to a different number, for example, 15, I need to stop running it that way, sorry. Give that a minute to load again. I'm not sure why if I click Control Enter to run the code, it seems to keep reloading the packages, which is odd, so I'll stop doing that. But yeah, if you change the number of breaks, you'll see the way that the crime distribution and the frequency looks completely different. You know, if we change the breaks to something quite dramatic like 3, no, then you'll see the way that this like frequency changes, right? And this is important because we are basically like dictating what our audiences will see and interpret. So let's go ahead and look at those 3 types of classification methods. Again, we're just going to be using the TM shapes by calling on our shapefile, which is that new aggregated LSOA. And we use a function called TM fill. We're calling on our crime count by this variable here. And this is the function that allows you to choose which classification method you want to use. So in this first plot, I'm looking at k-means. In the second plot, I'm looking at the Jenks. And in this third plot, I'm looking at the standard deviation. I'm also calling these into separate objects called A, B, and C, so that we can basically plot them all together in one plot. So let's go ahead and run that. And I'm going to change the viewpoint to static, so that's changing it back to plot. And then I'm going to use the tmap_arrange function to basically allow us to plot multiple plots in one image. So if we go ahead and run that, you'll see that we now have our 3 plots with the different classification methods. And what's important here is to basically look at the way that those intervals have changed. And it basically kind of like, you know, it changes our interpretation of what exactly we're reading because it shows that different areas have arguably different higher levels of crime counts in these areas. So it's really important to like understand the meanings behind these classifications and to then allow us to like interpret these correctly. Yeah. Another little useful function of the tmaps package is the tmaps_facets function. And this allows us to basically produce side-by-side maps, also known as small multitudes or multiples. It's very similar to the facet grid function in ggplot, if you're familiar with that. But it's basically defined by a categorical variable. So in this example, I'm using TM facets to separate the map into multiple components by the LSOA. This isn't the best example of a categorical variable, but if you combined this shapefile with something like urban and rural data, so you typically have like a binary data set that will tell you whether this LSOA is urban or rural, this would be a great example to use the TM facets plot. But currently I'm just going to be using the LSOA variable as its like reference point, but I just wanted to show you what this might look like. So if we go ahead and run this, it might take a while because we're looking to make multiple plots together. This basically just allows us to put all those individual areas into one map. So, you know, if you were interested in exploring maybe just a handful of LSOAs, you know, maybe you were looking at a really niche project, then this would be a great way to visualize that data. And again, if you had a variable like urban or rural, then you would simply just have 2 plots side by side that allow you to show the differences in crime counts across this like urban and rural distinction. Just checking the time. Okay, yeah. I will run through this quickly, but this is just some additional map layouts and styles that you can use to make your maps a little bit more visually appealing. So you can change the map style by using the tm_style function. Oh, maybe I've got that wrong, but it's given us options for different color styles. So why don't we go ahead and try maybe the cobalt function and see what that looks like. No, I don't. Okay, yeah, so this is just letting you change the map style. I thought that would have been effective for the colorblind palette, but maybe I've spelt that wrong or maybe I've put that in wrong. If anyone is familiar what the correct style is for the colorblind palettes, just let me know. Um, what other option did they have? Was there a grey there? Did I see grey? No. Yeah. So we do have a grey one as well. So yeah, there was loads of listed there, weren't there? You can also go ahead and add map legends. Like so. So this gives us, again, something else to just improve that visualization. And you can also add things like compasses, scale bars, and grids. So I'll go ahead and add that as well. Okay, object SBW not found. Just checking if I spelled anything wrong here. Strange, this was working yesterday. I feel like I might have object SBW. Hmm. Oh, that's strange because I really do like the little compass image that they have. But these three would be those for that. So it's the compass, the scale bar, and the grid. Um, I wonder if I've just failed to load a package. If you give me a quick minute, I will see if I can fix that error. In fact, what I'll do is allow you guys to move on to activity 2. What I want you to do is explore some of the different classification methods, such as the B cluster and the H cluster, and I want you to look at the differences between the two. If you need help on the different methods available, you can use this function here, tmap_package, or in the search bar here, you can also just simply search the function itself. So if I search B cluster, and it tells you that this is bag clustering. If you search H cluster, that this tells you that this is the hierarchical clustering. So I want you guys to just have a go at exploring these two types of classification methods. I want you to call them into two objects called H and B, and then I want you to plot them together using the tmaps arrange function. And then I want you to have a go at plotting an interactive map, specifically looking at the B class classification. So I'll give you maybe just about 5 minutes to go through this activity yourself while I have a quick look at that error that we just stumbled across, and then I'll talk through both. So I'm just going to mute myself and I'll be back in a few minutes to discuss the answers to activity 2. All right, so hopefully that's given you enough time just to work through this activity. I'm gonna just talk through the solutions for these. So the first step was to call onto a new object called H and define the hierarchical clustering classification to see what that difference would look like. So the first step is to call on your shapefile. Your next step is to fill this with your desired variable. In this case, we're using our count. And then you need to define the type of style we're using, which I showed you was called bclust. We then wanted to do the same, but for our, oh, sorry, let's make sure let's do bclust with bclust, that would make sense. And then we'll do H with our hierarchical clustering. So again, we call on your desired shapefile. You then call on the variable that we're working with, and then we call on the type of style that we're using. In this case, we'll use the hierarchical clustering. You then wanted to use the tmaps arrange function to basically plot these together. So this would be as simple as calling in those new objects that we've created as H and B. I then mentioned to create an interactive map of this. So we're going to set the tmap to view. And again, we are going to simply call on our LSOA. We're going to fill this by the crime count. And I think I asked you to have a look at the interactive one for the bagged clustering. B cluster, like so. So let's go ahead and run that. It's really quite irritating that it's loading all the packages every time I load a chunk of code. A bit strange, but it's working. So just give that a minute. So that's perfect. So here we have two images that show our bag clustering, so our hierarchical clustering and our bag clustering. So the differences between the two is that the hierarchical clustering generates the breaks using what we call, hierarchical, and the bag clustering generates the breaks using what we call bag clustering. And again, if you wanted more information about the differences between the two, you can use the help function here, and it'll tell you a little bit more about like the stats and the split between the two. All right, so that brings us to the end of topic 2. I'm just wary of time, so I'm going to move on to topic 3, which is looking at our census data set. In this section, we basically incorporate some census data onto our shapefile so that we can calculate and explore the differences between the crime rate and the crime counts. You might be thinking, like, why? What's the difference between the two? What is a crime rate? Well, a crime rate is best understood in totality as crimes per 1,000 residents as per the latest official census. Using a rate rather than the count basically reduces the statistical bias and reduces the effect of what we call the modifiable areal unit problem, which we looked at yesterday. So it's known that the crime rates vary in some populations and in some periods, and the prevalence of crime is much greater than in other populations and at other time periods. So accounting for these findings is, really important, because if we can understand the causal process that underlies this variation, then we may be in a position to enact policy change that can then bring about changes in the volume of crime in society at any given point in time. So for this workshop, for this section, I've downloaded both the residential and the population statistics from the CCAN portal. Again, if you want information about how I downloaded that data, that is found within the data folder called Downloading the Data. So we're going to first read in our population statistics. I'm going to first just read in the residential population statistics. Just to make you aware, the residential population simply reflects the usual activity of an area, whereas the workday population reflects the people who work, those who are resident in the area, and those that either work from home or who do not work. Arguably these two population statistics are limited because they don't include activities other than employment. So when conducting your own analysis, it might be accurate to use something like the total LSOA population, because the workday in the residential only reflects a partial population. But if your interest was in understanding employment trends with crime, then these would be suitable. So first step is to read in that residential population. Again, this bunch of code here isn't completely necessary to know for yourself. This is just some pre-processing that is needed as we're downloading this from a URL link. But this bit of code here is extremely important. So what we're doing is reading in our URL file, cleaning the names again, so making them all undercase and adding an underscore. I'm removing the first, I think it's the first 7 rows of data because they basically just included like all the syntax and information about the data set that isn't the rows of data. And this included rows 56 and 57 as well. I then renamed some of these variables because they weren't very clear in the data set, in that the variable was originally called x2, but this was in reference to the LSO name. And then we had this rather long variable here, which just indicated the name of the LSOA. So again, I changed this to name, and the column x3 represented the residential count, so I changed this just to res count. And if we look at the first few rows of the data set, you can see that we have those 3 new variables here. So this is our residential population for each area in Surrey Heath. Our next step would be to join these new statistics to our previously created shapefile named the Surrey LSOA. And again, we do this by using the left join function in the Diplo package, and we attach them by using the same LSOA codes. So I'm calling this onto the function, sorry, the data set Surrey LSOA, using the left join function, calling on our shapefile, calling on our residential count, and basically telling it to link them by using those 2 same LSOA codes. So let's go ahead and do that. And then let's go ahead and have a look at what we're looking at. So as you can see now, we have our count variable. So this is our original crime count in that area. But we also have this new variable added to our shapefile called the residential count. I will just open this up actually so it's a little bit clearer for you. And we scroll along, and you can see we have that new variable now added to our shapefile. In order to work out the crime rate, you do this by dividing the number of reported crimes by the total population and then multiplying by 1000. So for our data set, we take the count variable, we divide this by the residential variable, and then times this by 1000. We're using 1000 because this is the average population of an LSOA. If you were working with, if your unit of analysis was wards, then you would need to get the average population of a ward. If your unit of analysis was a country, you need to get the average population of the country, and so on, so on. But this is the average population of an LSOA in the UK. But just remember what effect this will have on your rate and then how this interprets across your results. So here we are creating a new variable crime rate in our shapefile. So what I'm doing here is calling on our shapefile. You call on this again so that you're not overriding the dataset. And we're using the mutate function from the Diplo package to basically create this new variable called crime rate. And we create this variable by running this little bit of calculation here. So we're basically dividing our crime count by the residential count and timesing by 1000, which will give us a crime rate. So let's go ahead and see what that looks like. And let's have a look at our variable again. So again, we've got this new variable here added called crime rate. Let's open up Surrey, scroll along, and we have this variable called crime rate, which is a much better representation of crime compared to the raw data because we're comparing it against population statistics. Again, as I mentioned, rather than residential count, you could use something like the total LSOA data, and this would give you a much more like generalized picture of crime. But this is giving us a generalized picture of crime against employment trends or population trends. So let's go ahead and explore what these trends look like using ggplot and tmaps. We've done this multiple times now, so we're going to just run this code. We're plotting this over a reference map And rather than using that count variable, we'll be using the crime rate variable that we just created. So let's see what this looks like first using ggplot. So in plot one, we now have this crime rate. And if you compare this to the original file, you'll see the original plot where we use the crime count, you'll see some differences in this like gradient. And then we have this kind of more defined plot again of our crime rate. The main difference between the two is that we're just filling this with the different variable that we created. What about with T-maps? Let's have a look what this will look like. In the first plot here, we're calling on the crime rate as the main fill object, and we're using the quantile classification system to do so. And then I've gone ahead and had a look at what this will look like as an interactive map as well. So here's our crime rate. Sorry, that's meant to say 1000. So let me just change that. Our crime rate per 1000. No. And yeah, there we have an interactive map of our crime rate. Again, you can, zoom into this, you can view the different areas, etc. Let me just get rid of this. I'm going to briefly talk about the cartograms, but unfortunately, I won't be able to run this chunk of code because it will just take too long, unfortunately, and we don't have that much time left. But a cartogram is basically a type of map where different geographic areas are modified based on variables associated to those areas. And there are two types of cartograms, which are contiguous and non-contiguous, and this just means that they share like a common border. But you can use the cartogram package in R to basically allow you to build a cartogram, and it requires a geospatial object as an input, and then you use a numeric variable in that data slot. But yeah, if you've got time yourself, I would suggest just uncommenting these and running this. But I just remember that this was taking far too long when I had to do this myself. So yeah, I will skip that for now, and I'll move on to our activity 3. In this section, well, in the above section, we successfully looked at the residential population. So I'm going to give you guys the opportunity to explore some of the stuff we just learned, but using the workday population, which arguably is like it's the economic activity variable. So your first steps is to read and clean that data. So the only difference here is that we're calling on a new object called workday count, and as you can see, we're calling on the workday population Excel file. So you can go ahead and just run that code, and that'll save you having to do any pre-processing. And from there, you then need to join the data set to our Surrey LSOA. And we do this again by just using that left join. We call on our shapefile, call on that new population statistic. So this instance is the workday. Let me just show you what that'll look like. So this is our work count rather than our res count. And we are going to ask R to join this again by the same LSOA code. So we'll run that and we have a look at Surrey LSOA. And now you can see we have another variable added in here called work count, which is our workday population. So from here, now you have your new, or you have your updated Surrey shapefile with the workday population. Have a go at working through these activities. So the first thing I want you to do is calculate the crime rate using the workday population. And I've got some of the code for you here, so you don't have to type it all out. Then you can plot this using ggplot, plot this using tmaps, And then I want you to plot both maps together. So that's using the tmap arrange function to compare the workday population with the residential population. And again, I've just also commented out the options for the cartograms, just because it will take too long. I might have a go at loading it now while I give you guys, I'm going to say 5 minutes just to fill out this activity. So I'll be back at 25 past to discuss the answers for this activity. All right, hopefully you've had enough time to fill out that activity. I've just having a look at the cartogram code and it does seem to work. I remember it taking far longer to load the required statistics before, but obviously not. So I'll go back and explain what a cartogram is in a bit more detail and why you might want to use this as a type of visualization. But I'm going to just run through the activity first. So the first step was to calculate this crime rate and assign it a new variable, named it crime rate 2, just so we're not overriding that original variable. So as we did for the residential count, you simply want to divide the crime count by the oh, have I named it? Um, oh, sorry, by the work count. That's what we're. And then we want to times this by 1000. So let's just load that to make sure that works, because no, I don't want to upload it. This is really irritating me. I don't know why it keeps loading the libraries all the time, but if I, um yeah, so that should work. Let me just make sure I do have that variable in here. There's not any confusion. Yeah, it is named work count, isn't it? Yeah, so that should work. If we scroll along, yeah, there's our crime rate 2. So this is our workday population, establishing a crime rate. So this is looking at like economic activity, really. And then we can go ahead and plot this with ggplot. The first step is to define your shapefile. So that's the Surrey shapefile. And then we want to fill this with the corrected crime rate. So in this instance, we're looking at the crime rate 2. We can go ahead and run that. Oh, this is irritating me. Right, I'm going to run it all at once so it doesn't keep doing that. But let's go ahead and just fill out the code for the rest of it. So we're going to be using the crime rate 2 variable. Spell that right. Going to use the style quantiles, same as we did before. I'm going to set the borders to alpha 3. That's just like the transparency of your borders, by the way. So if you wanted darker borders, then you simply increase that alpha number. And then let's compare the workday versus the residential population. So we'll keep object E as crime rate, which would be the residential population, and then we'll keep object F as the workday population. And then I've also said if you could basically plot these together. So this just involves calling on those 2 new objects. So let's go ahead and run that bit of code just to show you the difference between. No. Oh, silly, I've missed a comma there. Try that again. What's going on here? Um, I feel like I'm being a bit silly here. Crime underscore rate 2, that is the correct object, isn't it? Crime underscore rate 2. Maybe I've just spelt something wrong. Sorry, LSOA. Fill this with the crime rate 2. Did we get a plot? Yeah. Um, Let me just call that crime rate 2 as well, so we're not getting confused with that first one. Crime rate 2, crime rate 2. This should work. Let me know if anyone else is having any issues. This is really annoying. Um, if you just give me a minute while I TM fill. I think I know what I've done wrong. I think that these need to be in quotations. I think that's the solution here. I could be wrong, but yes, I would be right. This is problem with R, everything is so case sensitive, but yeah, this needs to be in quotations in order for that code to run. So let's just try that again. Oh, this is irritating me. Yeah, there we go. Okay, so that was just a syntax error, everyone. So make sure that you define the objects in quotations or you will receive an error. So let's try that. And let's go ahead and run all of this together one last time so that we can compare the differences between the workday and the residential count. Let's scroll down. There we go, much better. Right, now we have the workday population and the residential population here. So again, you can see that if we're using the residential populations, you know, from immediate glance, it would look like that some areas have higher crime rates compared to when working with workday populations. And this just kind of tells us sorry, my yeah, the workday population on the left represents the number of people present in each area during the work hours. The darker areas indicate higher and the lighter areas indicate lower. And then when we're looking at the residential population, which is on the right, the shading is the same. So the dark represents higher residential populations, but this is representing the number of people residing in that area, right? So yeah, this is just useful in understanding like commuting patterns and identifying areas where people travel for work and how this is affected by crime. Or sorry, how crime is related to those people who travel for work versus where they live. So if you had a research question about, you know, commuting patterns and using workday residential population would be a good initiative to do this. Um, I'm just wary of the time, so I'm going to make my way through the last section just because it is a little bit intense. If we've got some time at the end, I'll run through the cartogram explanations, but yeah, let's move on to topic 4, which is the spatial analysis. So this section covers spatial interpolation and heat maps using the crime data in Surrey Heath. The main goals are to basically estimate the missing crime values using spatial interpolation, and then we can visualize this crime intensity through the heat maps in ggplot and leaflet. We can then also perform spatial analysis statistics to compare data sets before and after imputation to see the differences in your results. So yeah, first things first, always load your packages. Obviously, it looks like my RStudio has been attempting to... I think this is a warning message just connecting to the GG spatial package. That's probably what that is. Bit annoying, but that's okay. Right, so yeah, spatial interpolation. If you remember yesterday, this is a technique used to estimate the unknown values at unsampled locations based on known data points. And this is useful in crime mapping when, there's data in missing areas, or if we want to create a continuous surface of crime intensity, or even if you wanted to estimate risk in locations where crime reports are sparse, then this would be an excellent technique. It basically relies on spatial autocorrelation, which assumes that the points close to each other tend to have similar values, and there are multiple different interpolation methods, but we'll be simply using the averaging approach based on the neighboring areas. So let's have a look at exploring our data. You don't need to reload in that crime data set because obviously we have that here somewhere. There's a crime data set still loaded in. So you can just skip over that bit of code. But we know that overall there are 6,806 observations. But what about just for Surrey Heath, which is a boundary area within the county of Surrey? The reason I'm minimizing the sample area is just to show you the differences and the key differences in what spatial interpolation will look like before and after our data set. So I'm going to go ahead and filter a specific area within Surrey, which is the Surrey Heath area. And we do this by using the filter, the str detect function, which is a natural language processing function that basically finds anything with Surrey Heath in this variable LSO name and creates this into a new object. So let's go ahead and run that. And let's see what this looks like. So we have this much smaller object now called Surrey Heath Crimes, which is noted just here. And yeah, so we've only selected this LSO names with Surrey Heath in them. So we can now see that there are 464 observations, and this is the individual crime counts across the boundary heath of Surrey Heath, right? This isn't the aggregated crime counts. So we need to do what we did before and basically group those crime counts from Surrey Heath and summarize them using the count function. So let's go ahead and do this. And I've just created a new object called clean crimed groups by LSOA, so this is a little bit clearer. So what can we tell? Well, we can see that there are now 52 observations, right? And in this case, this is representing the number of LSOAs in Surrey Heath. However, if we compare this to our shapefile of Surrey Heath, you'll know that there are 55 observations, which tells us that there are a few missing LSOAs. And we can run a spatial interpolation to account for these by estimating the missing crime counts based on the average neighbours of LSOAs. The first step is to identify the missing LSOAs, and we can do this using the function called setDiff. And I'm creating a new object called missing LSOAs just to make this a little bit clearer for us. calling on our new object that we created, which is the cleaned crimes, and also the LSOA code. So if we go ahead and run that, and we can go ahead and print these. So you can type print missing LSOAs. Go away. And you can see we do have, in fact, 3 missing LSOAs, which makes sense considering this object only shows 52 observations. In order to run the spatial interpolation on the averaging of these neighbors, we need to do some spatial visualization to kind of understand if these LSOAs do in fact have neighboring LSOAs to then establish a mean. And this is because if these LSOAs do not have any neighboring areas, we will not be able to establish a mean and therefore estimate a crime count. Obviously, the chances of an area not having a neighboring LSOA is very low, especially when we're working with multi-polygon data, but this is a really good technique to just understand. And we can do this by running a function called stTouches, and this basically just tells us which neighbors are in fact touching. So yeah, let's go ahead and run that. You'll see that we do get a new object. Oh, let's just print that. Yeah, so this tells us that there are 55 objects that are touching, which is good. And then it lists each of the LSOAs that are indeed touching. And now this allows us to identify the LSOAs with no neighbors. And this specific line here uses the sapply function to each element of the neighbors list. And this function basically checks if the length of each element is 0, which would indicate that an LSOA has no neighbors. So let's go ahead and run that. We then want to extract the indices of the LSOAs with no neighbors and then extract these to the corresponding LSOAs. We can go ahead and run that one. So yeah, now we have the LSOAs with no neighbors and the LSOAs with the LSOAs with no neighbors. If this object here, that the last object that we created, contains LSOA codes, then we know that the LSOAs with no neighboring LSOAs within your dataset. And this would mean that we know that this in fact does not have any neighboring areas, and therefore we can run some calculations on our neighboring areas to interpolate that missing value. So for each missing LSOA, which there were 3, we can find the neighboring LSOAs and calculate the average crime rate now. I've created a rather large function to do this in itself, and this function iterates over the whole list of your missing LSOAs that lack the crime data, and then for each of the missing LSOAs, it does this. I won't read this whole list out because it'll probably get a bit confusing, but it basically is just identifying the neighbours that share the boundaries. It gathers the crime counts from those neighbouring LSOAs, calculates the average crime rounds it up, and then prints this out for us. So this is the rather large function that will allow you to establish whether your missing LSOAs have any neighborhoods, and then establishes a average crime count for those missing LSOAs. So let's go ahead and run that. And now we have a new variable for each of those 3 missing LSOAs. Obviously, we need to think about the limitations when we need to think about the limitations when using interpolation, because how accurate would these results be in implementing policy or police allocation resources, for example. But yeah, you might have noticed that this new object now, cleaned crimes, has changed from 52 to 55 observations, allowing us or telling us that, great, there are no more missing LSOAs in your dataset. So what I want to do here is just compare the previous shapefile. So this was the Surrey LSOA. So this is the one that includes the missing data. and then the Surrey LSOO new, which we're going to create now, which is the no missing LSOA data. So let's look at how these might be different, both statistically and visually. So yeah, we're going to create these two new shapefiles that include the information about the missing LSOAs. Sorry, the one new shapefile, which is the Surrey LSOO new. So we're using the shapefile, and now we're using that cleaned crimes grouped by LSOA. So let's go ahead and run that bit of code. So now we have two shapefiles, one with the missing data and one without the missing data. The first step is just to compare these statistically. So this is kind of just comparing the means, comparing the mediums, and then printing these results. So you can see that the mean crime count in the original data, so this is with the missing, is 8.9, and the mean crime count for the imputed data is 8.8. So you see that mean reduces once we actually include the LSOAs with no missing data. And also this medium seems to increase when we include the data with no missing LSOAs. So again, this is just really important to think about what having missing LSOA, like missing crime data for your areas will do to your data set. We can also visually compare these. So we're going to plot the original data set with the missing values and then plot the data set with the imputed values just to see the difference in what this visualization might look like. So let's go ahead and run that. So in this first image, you can see that we have those three missing LSOAs that we've been working with pretty much this whole workshop, and the crime count situates from 10 to 30. In this image, you can see that our missing LOAs have been imputed, and we have a nice, clean, and completed map of our area. And yeah, this heat map basically just allows us to see whether, the new estimated values make sense. So we're now going to move on to making some heat maps. I'm now going to look specifically at antisocial behaviour across Surrey Heath. There's a little bit of data preparation needed, so this just involves pre-processing the data. So we're going to filter for antisocial behaviour. Again, only selecting for Surrey Heath. I'm going to group those crimes by LSOA and summarise. Sorry if this is very repetitive, but this is the kind of steps you need to do in order to start understanding your crime data a bit better. So we're going to run that whole chunk of code above, but specifically on an antisocial behaviour data set. So let's go ahead. And this is also accounting for the missing LSOAs. So we've got that for loop here that shows us how we establish the average crime count using its neighbours. So let's go ahead and run that. And now we have this new object called ASB, which is the antisocial behaviour shapefile, which includes the imputed values and is only looking at, the antisocial behaviour. We can use ggplot to go ahead and create a heat map visualization of this distribution of antisocial behaviour. This uses the magma colour palette and ensures that the visualization is both attractive and accurate. So let's have a look at what this will look like if it wants to run. Fab. So now we have this heat map. Oh, sorry, yeah. So now we have this heat map and it allows us to get a better visualization of our data. Are the crime patterns smooth or abrupt? Are there any large areas of missing data, or does the map highlight expected crimes hotspot areas, right? And this is where you have to start thinking about how you interpret your data to an audience. Quickly going to show you how we can map this in Leaflet as well. We use Leaflet for interactive maps, and it basically allows you to view those multiple polygons based on that crime intensity again. So I'm going to go ahead and run this chunk of code, and this brings us into, oh, that's incorrect. This happened last time and I ran it again and it just happened to work. So let's see. There we go. Yeah. Run it twice if that does that. This is only because Leaflet works with GG spatials, which means they're connecting to other softwares to basically establish this base map that allows you to be interactive. So sometimes it can lag. But yeah, this gives us a really cool, and again, another way to show our interactive map counts. So it's interesting to note that this area here seems to have the highest amount of antisocial behavior, even with those imputed areas that we can see. Um, and this area would be that LSOA here. Yeah. I'm going to run through this section rather quickly because I'm just looking at the time, but I also wanted to show you how you guys can start to look at more than just 1 month of data. Obviously, we've only been looking at February 2024 and specifically just been looking at a few types of crimes, right? But I'm going to show you how you can dynamically load in the 12 months of data set. So if you open up crime data, you can see that each month here represents one month of data. So I've created some code for you here that basically allows you to list all the 12 months and aggregate this into one data set. So you can go ahead and run that chunk of code here. And this is just some pre-processing, so it's not entirely necessary to know. Oh, what's that? Oh, it's either the tidyverse or the FS package that needs loading. We assume it's going to be the FS. Yeah, there we go. And now that is reading and merging all that crime data from the last 12 months. And it will take a while because it's just reading in quite a lot of data here. Shouldn't take more than a minute. Yeah, we're getting there, getting there, getting there, getting there. Fab. That's loaded in all that data. You can see we have this new object here which has 65,000 observations, which is why I was working with only 1 month of data at the beginning because it would have been difficult to basically show you how spatial interpolation and the autocorrelation works on such a large data set. But yeah, our first step is just gonna filter and aggregate these again, just to look at antisocial behavior crimes, just so it's a little bit easier to explore these trends. So you can just run this chunk of code here for you. All I'm doing is aggregating by LSOA and specifically by month. And then I'm creating a data column for the time series plotting by using the as.date function. And I'm asking it to call on each specific month as a marker in the time series plot. So you could first, quite simply, just plot the individual LSOAs by the antisocial behavior trends. As I've noted here, it's messy but insightful. So let's have a quick look at what this will look like. So this gives us our antisocial behavior trends over time per LSOA. In this plot, each line represents a different LSOA. Obviously, looking at this is a really kind of poor visualization of antisocial behavior. The only thing that does really tell us is where there's a cluster of where our antisocial behavior clusters, and it seems to sit around somewhere between, I don't know, 3 or 5. It seems to be where that's like the average number of ASP instance, right? But this plot isn't really telling us much. I would never give this plot to anyone to interpret or read upon. So we can go one step further and basically aggregate the ASB trends. So we sum up all the ASB counts across each area across each month, and this will give us a far more readable plot. So let's go ahead and do that. So this gives us an aggregated ASAB by each month and over time. Bear in mind that this is only from 2020, 2023 to 2024, so this is just 1 year of data. But you can see that in, I guess this is May. Yeah, in May, we have the highest amount of antisocial behavior, and September seems to be the lowest month of antisocial behavior, followed by January. And this could be affected by things like weather, for example. In the warmer weathers, there are more people out and about. Arguably could be affecting the number of antisocial behavior influences that happen. And lastly, I just wanted to show you a um, rolling average, or a smoothing, as we call it, is a way to um, basically get a better averaged visualization of our plots. And we use this rolling average function. I believe it's from the FS package to smooth our data to create a much more to just smooth those fluctuations and reduce the variability in our data set. Oh, roll mean. What package have I forgot to load here? Oh, I think it's actually the zoo package. This should be a base package in R, so you shouldn't have to install that. Apologies if you do, but the package will be the install dot packages by quotations and zoo. Let me just make sure that that does work. No, thank you. Yeah, fab, that's worked now. So the rolling average is actually part of the zoo package, so you might need to just install that independently. That shouldn't take too long in Colab, and it definitely wouldn't take too long in R in itself. But we can go ahead and plot that rolling average trend. So as you can see, we've got this aggregated trend line that shows us. It basically removes any unwanted variation in our time series plots and gives us a much smoother trend about the total number of ASABs. Now, I'm just noticing the time, and we're coming up to exactly 2 o'clock, which is where our workshop is due to end. So I'll just leave you with a few things to take away with yourself. There's an optionals activity here, which will allow you to explore the antisocial behavior data with the missing values, just to see the differences between the two. So if you've got some time, feel free to finish this activity yourself. What I will do is complete the task now, push the changes to GitHub, and you'll be able to see those. This activity has been, it will be completed for you. And on a separate note, there is one last additional topic section. So for anyone who's looking for a bit more advancement in plotting data, then there's some pretty cool features here, such as connecting ggmaps and ggplot using Google AI. So this basically allows you to make some plots using Google, which is really cool, but there are lots of steps required to kind of get yourself set up here. But I've written everything out for you here. And I think there is some information about binning as well, which is thought of a two-dimensional histogram. But yeah, and there's a bit more about interactive maps and a bit more about some other important functions such as jittering, which is a technique used by police to geomask their data. But yeah, just given the time, I'm gonna call it an end there. And I'm going to head back to the slide. Let me just turn my video back on. I'm going to have a look at the questions and Q&A, see if I've missed anything. But yeah, thank you all for taking part in this workshop. I hope you found it informative, and I hope you could learn a bit more about how to join empty spatial data with shapefiles, We learned how to join this to census data, and we learned a little bit about the differences in mapping raw crime counts to compared to crime rates. So yeah, if you could all complete our short survey as you leave, that'd be great. Um, if you have any further questions, please feel free to send me an email and I'll do my best to uh, send out a response to you. But yeah, I think that's everything, unless I'm missing anything major in the chat. But thank you so much for listening. I hope that was useful. Again, I feel like I rushed through a few parts there, so if you want some more information on anything, just let me know and I will send you, yeah, feel free to send me an email.